In the last two videos we learned about periodic functions and how to describe them mathematically and analyze it by the Fourier analysis and how they are composed by the Fourier series. But what's about non-periodic signals? Example is this rectangle function. It is 0 all the times except somewhere around the origin where it takes a certain value and goes 0 again. This is a non-periodic signal because it does not repeat. So in this video we're gonna learn about how to describe this signal mathematically and analyze it, similar to the Fourier analysis of the second video. You will find additional material in the lecture notes in chapter 2.3, and this is where this video is based on. So for periodic signals, we use the Fourier analysis to obtain the spectrum or the spectra. And the Fourier series yields the periodic signal again. So what's about the non-periodic signals? We also want to analyze its spectra and therefore obtain its frequency components. But is it possible? Yes, it is. And there is a method to analyze the frequency components, and this is the Fourier Transform, which we are gonna talk about now. And the other way back to get the non-periodic signal from its frequency components is just called inverse Fourier transform. Here the Fourier transform is in fact a special case of the Fourier analysis and Fourier series. The Fourier analysis and series work on periodic signals, but for non-periodic signal you can imagine that the period of the signal goes against infinity. And this is a special case of the Fourier analysis and brings us to the Fourier transform. The exact derivation is shown in the lecture notes in chapter 2.3.1, so you should refer to the lecture notes for details. Here in this video I just give you the solution and the definition of the Fourier transform. The Fourier transform is defined by the integral over our non-periodic signal and this term. The inverse Fourier transform is given by we can also use an operator. It's this calligraphic F, which stands for our Fourier transform. We'll use this notation a lot, and we use this calligraphic F with an -1 to define or to write the inverse Fourier transform. If you have a look at the literature, you will find a lot of or various definitions of the Fourier transform and inverse Fourier transform. There are 3 definitions which look quite the same, but they are distinguished by the frequency value used. So in this lecture we are going to use the angular frequency, but there are other forms which use the ordinary frequency, for example. So don't get confused by it. So here in this lecture it's the angular frequency. You will find it here and here. And if you take a look at the definitions of the Fourier transform and inverse Fourier transform, you see that they look quite the same, but the only difference is that the Fourier transform uses a minus here, and the inverse Fourier transform uses a plus here, and the inverse Fourier transform has also this prefactor. So using the Fourier transform, we can obtain the frequency components of a non-periodic signal. And there is a major difference to periodic signals. So periodic signals had a discrete spectrum. So remember, the frequency parameter was n, and n was an integer. So 1, 2, 3, and so on. So the frequency components were just defined at some discrete values of n. But now have a look at the definition of the Fourier transform. The X here. And here we have the omega as our frequency parameter. Or frequency variable. And in this case it is for non-periodic signals, it is not discrete, it is continuous. So our frequency variable is now continuous. It can be any value between minus infinity and plus infinity. So there's no restriction. And that is the major difference between periodic and non-periodic signals. Now let's have a closer look at the spectrum of a non-periodic signal. So let's take our example from the introduction again, the rectangle function, which was 0 at all times, except somewhere around the origin. You will find a mathematical consideration in the lecture notes, so we won't repeat it here. And now let's analyze this function, which is given in time in the frequency domain. So let's analyze its frequency components. So now we use the Fourier transform. And then we get, like for periodic signals, we get an amplitude spectrum. And we will get a phase spectrum. So as the Fourier transform is strongly related to the Fourier analysis, and we have an input function given as a pure real valued signal, we can at this point already tell about the symmetry roots of the spectrum that we are going to receive. So the amplitude spectrum will again be even, and the phase spectrum will be odd again. This is what we already know. So, and yeah, the derivation of the spectra is given in the lecture notes. I just paint the solution here. The spectrum of a rectangle function is a sinc function. Yeah, there are some other parameters here, but it depends on the frequency variable omega. And as you can see, the amplitude spectrum is even, it's symmetric, and we also expect that the phase spectrum will be symmetric. But odd, so it will be symmetric to the origin. And in fact, it is symmetric and odd. So this is how our spectra look like, and we see that the spectrum is continuous, so there are no discrete points anymore, so the spectrum is defined on any point on the frequency axis. Yeah. So now you see two representations of the same signal. So we have, first representation is here on this side, is our rectangle function, which depends on the time. And we have the spectrum here. Which depends on the frequency variable. Both representations are the same signal, but there are two representations. So the first representation is in the time domain, because it depends on the time, and the second representation is the frequency domain. And as I said, they are the same signal, and they are connected by the Fourier transform or the inverse Fourier transform. Or for periodic signals by the Fourier analysis and the Fourier series. So now you see that we have two representations, but why do we actually care about these representations, or why do we have these two representations? What is the purpose for this? Imagine you have some kind of mathematical problem and you want a solution. But generally this solution is very hard to find. So this is exactly the point where our transform come in. We transform our problem into another representation. It's still the same problem, but it is written in, or it is expressed in another mathematical form or domain in this case. And in the new domain, the problem is very easy to solve. Now we have a solution which we have found very easily, and we just transform back to the original domain. By the inverse transform. And now we have just found our solution, but had a very easy way to solve it. And this is exactly the reason why we do transforms. Here again, so we have a problem here in the time domain, where it's very hard to find a solution, and we transform it to the frequency domain. And we will find an easy solution. So later we will see examples which prove that solving a problem in the frequency domain is really easier, and that it's worth it to do the transform and inverse transform.